Like its name implies, a switchyard is simply an enclosed yard full of switches. The switches you see here are larger than the light switches you have in your home, but fundamentally, they serve the same purpose. They open and close electrical circuits. Now, if we look at the T&D system as a whole, we can see where the switchyard fits into the picture. The switchyard connects the electricity generated at the power plant to the transmission system and directs the electricity to the lines that will carry it where it's needed. As we'll see later on, most switchyards are connected to several alternate sources of electricity and several alternate loads. The switchyard is used to select the source of electricity and the path it will follow along its journey. Often, the conductors leaving the unit transformer carry power directly to a switchyard located nearby. The conductors, supported by metal structures, carry electricity from the unit transformer to the major components in the switchyard. Switchyards usually contain two main types of switches: circuit breakers and air disconnect switches. Because the electricity is usually transmitted by three phases, you'll often find these devices in groups of three. Circuit breakers, like their name implies, are often used to open or break an electrical circuit. The switch mechanism is enclosed in a housing. Like the circuit breakers in many homes, these breakers can also be equipped to automatically interrupt the flow of power when certain electrical problems are detected in the transmission circuit. Breakers automatically open, stopping the flow of electricity and preventing damage to equipment and components. Disconnect switches serve a different purpose. They're used to isolate equipment from maintenance or repair. Opening a disconnect provides a visible break in the circuit. If you're working on a circuit that's supposed to be de-energized, you'd open the breaker and the disconnect. That way, even if the breaker is accidentally closed by a remote signal, the open disconnect keeps you and the circuit isolated from voltage. Now we're going to take a closer look at some of the common types of breakers and disconnects. Oil circuit breakers, commonly called OCBs, and sulfur hexafluoride or SF6 breakers are different solutions to the same problem. The problem they solve is how to extinguish an arc, the electrical spark that results from opening and closing a circuit. The oil circuit breaker found in switchyards are usually housed in large tanks like these. Now, like other circuit breakers, they normally sit side by side in groups of three on a steel and concrete base. This typical OCB has two large bushings mounted on top. Conductors are connected to the bushings on each side of the tank. One conductor goes to the source and the other goes to the load. SF6s have similar bushings and conductors, but their enclosures come in many different shapes and sizes. Both types of breakers have features that help extinguish electrical arcs. To see the differences, let's have a look inside. This is a simplified example of the inside of an OCB that hasn't been filled with oil. These switch contacts can be closed or opened to connect or disconnect the circuit. With no oil inside, opening and closing the breaker makes a considerable arc. Submerging the contacts in oil helps minimize arcing and its destructive effects. The oil helps extinguish the arc that's created by disrupting the flow of electricity. For contrast, let's see how an SF6 would do the same job. This is a simplified version of the inside of an SF6 breaker. The contacts are in the closed position. There's no oil surrounding the contacts. Instead, there's a reservoir of SF6 gas, a special insulating gas stored under pressure. When the contacts open, the arc is snuffed out by a high-pressure blast of gas, just like blowing out a candle flame. The contacts open, breaking the circuit without any major arcing inside the housing. The circuit breakers we've investigated so far are just two of the many types that you'll find in switchyards. By looking at SF6s and OCBs, we've seen two very different ways that circuit breakers can extinguish arcs when circuits are opened and closed. On the other hand, disconnect switches don't need many special features for quenching arcs. Circuit breakers do all of the actual switching. Together in a switchyard. In this simplified diagram, we're looking at a single line in the switchyard. Now, as we've seen, breakers and disconnects usually come in groups of 3. Electricity comes in here, current flows through the disconnect, through the circuit breaker, and through the second disconnect to the load. In this case, the load is connected to a transmission line. Usually, we have several sources of power and several loads. In a switchyard like this one, we can select the source and the load in a number of different combinations. Now once again, to get an idea of how this works, we'll go to a simplified example. In this example, we're using single lines to represent the 3 conductors you'll see in actual switchyard circuits. Now these symbols represent unit transformers. Each one is a separate source of power for the switchyard. Right now, these circuit breakers are in the closed position. These disconnect switches are also closed. The breaker in the middle and both of its disconnects are in the open position. In this situation, each unit transformer is supplying power to a separate transmission line. There's no connection between them. Now, to see how we can use the switchyard to redirect the flow of power, let's say that this transformer has to be taken out of service. If the other transformer can handle the combined load, we can switch things around so it supplies both transmission lines. The first thing we have to do is tie both lines together using this cross connection. We close the disconnects and then close the circuit breaker. The 2 transmission circuits are now electrically connected to each other and both sources. The next step is to remove this source from the circuit. First, we open the breaker. Again, by using the breaker to open the circuit, we minimize arcing. Then, once the circuit is broken, we open the disconnect. Now at this point, a single transformer is supplying both of the transmission lines. The other transformer is completely isolated from the circuit. It can now be disconnected from the source without interrupting the flow of electricity from the power plant to the consumer. In the example we've just seen, we examined a relatively simple switchyard arrangement. We had 2 sources and 2 loads. In many switchyards, the actual situation is much more complex. There are more sources to choose from and more alternate transmission lines for sending power to the rest of the T&D system. After all, the switchyard is a major connecting point. It connects the various power plants in the local area and connects the local power system to the larger power grids. Power travels to the transmission lines, advancing one more step along its journey to the consumer. When we return, we'll follow along and take a look at the structures and the equipment that form the transmission lines of the T&D system.